If I ask you what the natural numbers are, you might say 1 is a natural number, of course 2 is a natural number, 3 is a natural number, and so on, infinitely. But there is a problem with that answer, because you're just listing the elements of the set of natural numbers, not defining what the set itself actually is. So before enumerating its members, you first need a clear definition of the set. So let me ask again, do you really know what the natural numbers are? Advanced math concepts can be incredibly difficult to grasp, so before diving into formal definitions, I will approach the ideas in an intuitive way. Let's start with something everyone understands, which is counting. Suppose you want to know how many coins you have. How would you do that? First, we need language to describe quantities. If you have this many coins, we say you have 1 coin, but if you have this many, we say you have 2 coins. Now, observe something interesting. If you separate the 2 coins and count them individually, you have 1 on the left and 1 on the right. If we introduce the idea of addition, which intuitively means combining things, we see that 1 plus 1 equals 2. But here is the key realization. These names 1, 2, 3 are just labels we assign. We could arbitrarily declare that this equals 3, so 1 plus 1 equals 3 and 3 plus 3 equals 4. Semantically, there'd be no issue. Names are conventions, yet while the words are flexible, the underlying idea remains unchanged. We can rename quantities, but the structure how these quantities relate persists. This is why formalizing the concept itself matters far more than the symbols we use. And this is where the true definition of the natural numbers begins, not with labels, but with the immutable relationship they represent. Until the 19th century, natural numbers lacked a rigorous definition. Many mathematicians attempted to formalize them, but their efforts fell short. That changed in 1889, when the Italian mathematician Giuseppe Peano finally established a complete and precise definition. But before diving into Peano's axioms, let's approach the idea intuitively. First, we need to ask, what fundamental properties should natural numbers have? In other words, what do we expect natural numbers to do? The first intuitive requirement is that natural numbers must have a starting point, a minimum element to begin counting. At first glance, it seems natural to choose the number 1 as this foundation, just as we did earlier with coins. But there is a problem. Defining the natural numbers by saying 1 is a natural number creates a circular argument. After all, we can use the concept of 1 to define the natural numbers if 1 itself is part of what we are trying to define. The key realization here is that this starting element, let's temporarily call it the element 1, is not the familiar number 1 we know from everyday counting. It's an abstract placeholder, a minimal object in the system with no inherent meaning beyond its role in the structure. This distinction is crucial. By treating the starting element as a purely formal idea rather than the intuitive number 1, we avoid circularity and lay the groundwork for a rigorous definition. Our first axiom for the natural numbers must assert the existence of a starting point. So our first requires that the set contains at least one fundamental element, which we will call the element 1. With just our first condition, the existence of the element 1, we could theoretically have a system where this is the only natural number. The framework would still be consistent, but it wouldn't capture our intuitive notion of numbers that continue indefinitely. To properly formalize the natural numbers, we need more structure. Let's return to our coin analogy. When we place 1 coin on the left and 1 on the right, we recognize this combination as 2 coins. Similarly, combining 2 and 3 coins gives us 5. This suggests a fundamental property we want natural numbers to satisfy: the ability to generate new numbers from existing ones. This leads us to introduce the successor axiom. We postulate the existence of a function s called the successor function with the following property. For any natural number n, the successor of n is also a natural number. At this foundation level, s is completely abstract. We only require that it produces another natural number. While eventually this will correspond to adding 1, we are not yet defining it that way. The successor could theoretically be any natural number. It could be n itself, a fixed number like 1, or follow some other pattern. The key point is that this function ensures we can construct new numbers from previous ones. These 2 axioms alone are insufficient to define the natural numbers, As we have already seen, they could lead to the conclusion that the natural numbers consist of only one element, thus we need more formal power. Intuitively, while we could represent any quantity of coins with just a single coin, the reverse is not true. We cannot express one coin in terms of any other quantity of coins. The reason is simple. It serves as the foundation for all other quantities. Abstracting this idea, we can state that this element, the element 1, cannot be constructed from other natural numbers. In other words, there exist no natural numbers whose successor equals 1. This becomes our third axiom. 1 is not the successor of any natural number. With this addition, we now avoid the trivial case where the natural numbers contain only the element 1. Since the successor of 1 must differ from 1 itself, we guarantee the existence of at least one other distinct element in the set of natural numbers. Returning to our basic intuition, we know that, in principle, there is no inherent limit to how we group or count coins. If we have a certain number of coins, we can always add one more, two more, or any arbitrary amount. In other words, natural numbers should be unbounded. You might assume our next axiom should be the set of natural numbers is infinite, but this is not precise enough. So far, the only natural numbers we have explicitly defined are 1, its successor, and the successor of the successor of 1, which can be equal to the successor of 1. The rest could, in theory, be anything. There is no inherent structure connecting them to what we already know. To resolve this, we must rely on a property that logically extends our existing definitions. Once again, we turn to the successor function. But how does this guarantee infinitely many numbers? The issue is that the successor function without constraints could create loops. For example, suppose n is the successor of 1, m is the successor of n, and n is the successor of m. This would form a loop, violating our goals of an endless non-repeating sequence. To prevent this, we restrict the successor function. If two natural numbers a and b have the same successor, then a must be equal to b. In other words, the successor function must be injective. This eliminates loops. In the earlier example, m and 1 share the same successor n, but since m is not equal to 1, this violates injectivity. Now we know 1 is a natural number, the successor of 1 is also a natural number distinct from 1, the successor of 1 is distinct from both 1 and the successor of 1. Because loops are not allowed, where does this process end? Well, it doesn't. Therefore, the natural numbers under these axioms must: first, contain the element 1. Second, every natural number must have a successor. Third, 1 is not the successor of any natural number. And 4, the successor function is injective, which implies there must be an infinitely many natural numbers. This system proves to be very powerful. We can even define the sum of natural numbers as follows. Intuitively, when we have 6 coins and not 4 more, the sum should simply represent counting them together. Formally, addition is an operation that maps pairs of natural numbers to natural numbers, with the crucial property that for any natural number a, adding 1 yields its successor. Importantly, we are defining the successor of a not as an arbitrary element, but as a concrete, uniquely determined quantity. When defining addition for arbitrary natural numbers, we state that a plus the successor of b equals the successor of a plus b. At first glance, this appears problematic. We are using a plus b to define itself. Then we have a problem. This foundation lets us build all other sums incrementally. Taking a equals 1 as an example, we know 1 plus 1 equals the successor of 1. Then 1 plus the successor of 1 becomes the successor of 1 plus 1, and so on. This recursive approach is not arbitrary. It perfectly captures the concrete process of counting physical objects like coins, where each addition represents appending another single unit to an existing quantity. We can now assign the familiar names to these numbers. The element 1 is just the number 1, its successor 1 plus 1 we call 2, the successor of the successor, whether written as 1 plus 1 plus 1, 2 plus 1, or successor of the successor of 1, we call 3, and so forth, for any natural number. Now, returning to our definition of addition, to compute a plus b for any natural numbers, first start from 1 and apply the successor function repeatedly to reach a. From there, apply the successor function b more times. The result is exactly what our definition of addition prescribes. Each plus 1 corresponds to taking a successor, mirroring how we intuitively count objects in sequence. This is remarkably powerful. We have taken our intuitive understanding of numbers and grounded it in rigorous formal foundations. Through this process, we have precisely defined the familiar set of natural numbers that everyone recognizes. But wait, this system is not yet the true set of natural numbers. While our definition of addition via successors of 1 aligns with intuition, there is a critical gap. Nothing in our 4 axioms prevents the existence of rough elements. For example, imagine a natural number x that is unreachable through any finite application of the successor function to 1. Such elements would behave like unreachable coin piles. In our analogy, quantities you could never obtain by accumulating single coins, which violates our intuitive understanding. The deeper issue is our inability to prove universal properties. For instance, in the concrete world, adding n coins plus 1 coin always equal to n plus 1 coins. In our abstract system, we had need to verify this for every natural number, individually, an impossible task due to infinity. Even commutativity, obvious when handling physical coins, becomes unprovable in our system. With our current axioms, we cannot prove that the left pile of coins plus the right pile of coins equals the right pile plus the left pile. But when we physically arrange coins, the order clearly doesn't matter. Yet our formal system is too weak to capture this obvious truth. Once again, we need more power. We need a property that allows us to prove a fundamental trait of all natural numbers. Specifically, the property that every natural number can be obtained by applying the successor function to the element 1 a finite number of times. With this, we have arrived at the final step in defining the natural numbers. The solution to this problem might seem sophisticated, but it's actually quite straightforward. The principle of induction. This axiom states that if we have a subset M of natural numbers, simply a collection of natural numbers satisfying 2 conditions. First, the element 1 is in M, and second, for any arbitrary natural number in M, its successor is also in M, then M must be the entire set of natural numbers. Let's verify this. Consider the set A, which consists of all successors of 1 ad infinitum. We already know by the second axiom that every element in A is a natural number. Now observe that 1 is in A by definition, and for any number in A, its successor is also in A, since A is constructed entirely by iterating the successor function. Since A satisfies both conditions of the induction principle, the fifth axiom forces A to be the set of natural numbers. Thus, every natural number can be obtained by applying the successor function to 1 a finite number of times. But wait, is it really that simple? Let's test this. Suppose we define another set B that includes all elements of A, but also introduces additional arbitrary elements like this. At first glance, B seems to satisfy the induction axiom. 1 is in B, and for any number in B, successor is also in B. Does this mean B is the set of natural numbers? Not so fast. If B is the set of natural numbers, we can revisit the fifth axiom with A. A is a subset of N, which is B here. A contains 1, and for any number in A, its successor is also in A. By the axiom, A must equal the set of natural numbers, but since the natural numbers are B, this forces A equals B, even though B contains elements like this not in A, a contradiction. Thus B cannot be the set of natural numbers. Now, what if we apply the same logic to A? Assume A is the set of natural numbers, and take a proper subset C of A. In other words, C lacks at least one element of A, this one for example. Does C satisfy the fifth axiom? Let's check. 1 belongs to C, correct? Now, if N belongs to C, then its successor must also belong to C. However, here's where the issue arises. Take the element immediately before the one we removed. This element is in C, but its successor is not, meaning C fails to satisfy the required condition. Therefore, C cannot be the set of natural numbers. We have now shown that if you add elements to A, you reach a contradiction when trying to prove that the new set is a set of natural numbers, but if you remove even one element, the resulting set no longer satisfies the condition to be the natural numbers. The conclusion is that the set of natural numbers is the smallest set that fulfills these two conditions. which is precisely A. This aligns perfectly with our intuitive understanding of natural numbers. But there's one more crucial point. Earlier, I mentioned that we need a property that allows us to prove something for every natural number, and guess what? Induction is powerful enough to do exactly that by its very definition. For example, take a property P of n such as this difference of squares. Now define x as the set of natural numbers satisfying P of n. If we prove that 1 satisfies P of n and a sum of numbers satisfies P of n, then prove that its successor also satisfies it, then x must contain 1, a number, and its successor, meaning x is the entire set of natural numbers. In other words, all natural numbers satisfy P of n. So the principle of induction used for centuries is now a fully rigorous mathematical process. As I mentioned earlier, this is the formal system of natural numbers that modern mathematics relies on. With this foundation, you can now prove fundamental properties like the associative and commutative laws for addition, the definition of multiplication, followed by proof of its associative, commutative, and distributive laws. Crucially, these properties cannot be proven without the axiom of induction. This makes the natural numbers not just an intuitive concept, but a powerful and precise mathematical system.